Picture a galaxy unlike any other, a colossal, glowing ring suspended in the black expanse of space, like a celestial crown spinning in slow motion. This is the Cartwheel Galaxy, one of the most bizarre and captivating structures in the known universe. Its striking ring shape, spanning over 150,000 light-years, isn't just a cosmic fluke. It's the result of a cataclysmic collision, a violent dance between galaxies that left behind a shimmering ripple of stars and gas. But what makes this galaxy truly extraordinary isn't just its appearance, it's the sheer number of mysteries packed into its swirling arms. From unexplained bursts of star formation to strange, shadowy voids where the laws of physics seem to twist, the Cartwheel Galaxy is a treasure trove of cosmic oddities waiting to be unraveled. Discovered in the mid-20th century, this galaxy immediately stood out as something otherworldly. Unlike the neat spirals or fuzzy ellipticals we're used to seeing, the Cartwheel's peculiar structure defied easy explanation. Astronomers soon realized they were looking at the aftermath of a cosmic train wreck. A smaller galaxy had plunged straight through its heart, sending shockwaves rippling outward like a stone dropped into a pond. That collision triggered a chain reaction of bizarre phenomena, from superheated gas clouds to pockets of space where time itself seems to warp. And yet, even decades later, this galaxy refuses to give up all its secrets. Every new observation reveals something stranger, something that challenges what we thought we knew about how galaxies live, die, and evolve. That's exactly why we're diving deep into the Cartwheel Galaxy today, to uncover the 30 most mind-bending phenomena hidden within its rings. Some of these mysteries might rewrite the textbooks, others could hint at forces we don't yet understand, and a few might just leave you staring at the screen, wondering how reality can be this strange. So buckle up, we're about to journey into one of the universe's most enigmatic corners where the rules are bent, the surprises never end, and every discovery feels like peeling back another layer of an infinite cosmic onion. By the time we're done, you'll never look at the night sky the same way again. The most striking feature of the Cartwheel Galaxy isn't just its size, it's that colossal, luminous ring wrapping around it like a cosmic bullseye. Picture a wheel spinning through space, its outer edges blazing with newborn stars while the center glows faintly with the embers of older ones. This bizarre ring structure, stretching across an unimaginable 150,000 light-years, is what makes the Cartwheel so unlike any other galaxy we've found. Normally, galaxies settle into predictable shapes, spirals with graceful arms, ellipticals like glowing blobs, or irregular clouds of stars, but the Cartwheel. It's a cosmic oddball, a shape so rare that astronomers call galaxies like it ring galaxies, and even among those, it stands out as one of the most extreme examples ever discovered. How did this giant ring come to be? The answer lies in a violent, almost cinematic collision. Millions of years ago, a smaller galaxy, perhaps a fraction of the Cartwheel size, slammed straight through its heart. Think of it like a rock hurled into a pond, sending ripples cascading outward. But here, those ripples aren't water, they're shockwaves of gas and dust compressed so violently that they triggered an explosion of star formation. The outer ring we see today is essentially the wave front of that collision, a cosmic tsunami frozen in time. As the shockwave expanded, it left behind a trail of superheated gas that cooled just enough to collapse into thousands of brilliant blue stars. That's why the ring looks so vivid. It's packed with stellar newborns, some only a few million years old, burning hot and bright. Meanwhile, the galaxy's core tells a different story. While the outer ring blazes with youthful energy, the center is quieter, dominated by older, yellower stars that predate the collision. They're the survivors, the original inhabitants of the Cartwheel before it was reshaped into this cosmic spectacle. This stark contrast between the frenetic blue ring and the calm golden core creates one of the most visually stunning phenomena in the universe. It's like looking at a galaxy caught between two eras, its past and future written in light. But here's where it gets even stranger. Most galaxies, even after a collision, eventually settle back into some semblance of order, not the cartwheel. Its ring structure has persisted far longer than models predicted, defying expectations. Some scientists suspect hidden forces might be at play, perhaps pockets of dark matter anchoring the ring in place, or lingering turbulence from the collision still churning the gas. Others wonder if we're witnessing a fleeting moment in cosmic time, a structure that will gradually fade as the galaxy heals. Either way, the cartwheel's ring isn't just a pretty feature, it's a cosmic puzzle, one that challenges our understanding of how galaxies evolve after catastrophic encounters. And that's just the first of its many mysteries. While the Cartwheel Galaxy's outer ring dazzles with newborn stars, its core tells an entirely different story, one written in the faint golden glow of ancient suns. Nestled deep within the center of this cosmic wheel lies a dense, enigmatic bulge of stars so old they predate the galaxy's famous collision. Unlike the vibrant blue star clusters bursting to life in the outer ring, the central bulge moves slowly, quietly, its stars orbiting in a tightly packed swarm that seems almost disconnected from the chaos unfolding at the galaxy's edges. What makes this region so puzzling isn't just its age, it's the way it behaves. Normally, a galaxy's core and its outer regions influence each other, with gravity maintaining a delicate cosmic balance. But in the cartwheel, the central bulge appears oddly isolated, as if it's marching to the beat of its own drum. Some astronomers suspect this disconnect might be due to an invisible anchor lurking in the heart of the bulge, a supermassive black hole, millions of times heavier than our Sun, warping space around it. Yet even that theory doesn't fully explain the bulge's strangeness. Observations reveal fewer young stars here than expected, suggesting something is suppressing new star formation. One possibility, the collision that created the cartwheel's ring might have sent shockwaves that effectively cleared out much of the gas needed to make new stars, leaving behind an older, quieter population. Another clue comes from the star's motions. They orbit faster than predicted, hinting at unseen forces at work. Could dark matter be concentrated here, twisting the rules of gravity? Or is the bulge's odd behavior a lingering echo of that ancient galactic crash, still reverberating through the core? Then there's the question of why this region hasn't been more affected by the ring's explosive star-forming activity. In most galaxies, massive stars die in spectacular supernovae, scattering heavy elements that enrich their surroundings. But the cartwheel's center seems strangely pristine, almost as if it's been shielded from these cosmic fireworks. Some researchers propose that the ring's outward expanding shockwave carried away much of the material that would have otherwise fallen inward, starving the core of fresh gas and leaving it frozen in time. Whatever the explanation, the cartwheel's central bulge stands as a cosmic anomaly, a relic of the galaxy's distant past, holding secrets about its violent transformation. Studying it could rewrite our understanding of how galactic cores evolve after catastrophic collisions. And with every new observation, this dense, ancient stellar crowd seems determined to keep surprising us, proving that even in a galaxy famous for its luminous ring, the true mysteries might lie in its shadowy heart. Beyond the Cartwheel Galaxy's glowing outer ring and its ancient central bulge, there's another enigmatic feature, faint, ghostly streaks stretching from the core outward like the spokes of a cosmic bicycle wheel. These delicate filaments, barely visible against the backdrop of swirling starlight, are anything but simple decorations. They're scars from the galaxy's violent past, silent witnesses to the forces that reshaped this region of space millions of years ago. Unlike the symmetrical perfection of a man-made wheel, these spokes are uneven, some thick and prominent, others wispy and fragmented. Their haphazard distribution hints at chaos lingering beneath the galaxy's mesmerizing beauty. One prevailing theory suggests these streaks are trails of stars and gas, wrenched from their original positions during the collision and stretched into these elongated shapes by gravitational tides. Imagine two galaxies passing through each other, their mutual pull twisting and warping the fabric of space, leaving behind these eerie contrails like celestial footprints. But the mystery deepens when you consider how they've endured. Normally, such structures would dissipate over time as stars and gas drift apart, yet here they remain, faint but persistent. Some researchers propose that dark matter, invisible and pervasive, might be acting as a scaffold, holding these spokes in place far longer than physics would typically allow. Others speculate that magnetic fields, woven through the galaxy like invisible threads, could be stabilizing the gas within these streaks, preventing it from scattering into the void. Even more puzzling is their uneven brightness. Some spokes glow more vividly with young, blue stars, while others are barely visible, dotted with older, dimmer stellar populations. This imbalance suggests the collision's shockwaves didn't ripple outward uniformly. Instead, they surged unpredictably, leaving pockets of intense star formation alongside quieter, neglected regions. It's as if the galaxy itself bears bruises from the impact, some areas healing faster than others. What's clear is that these spokes aren't just remnants, they're active clues. By studying their patterns, astronomers might unlock secrets about the original collision's angle, speed, and even the nature of the intruder galaxy. Every irregularity, every gap in their structure tells a story of chaos frozen in time, a cosmic detective story written in stardust. And like all great mysteries, the more we learn, the more questions arise. Why do some spokes curve subtly, as if tugged by unseen hands? Could there be smaller, hidden galaxies lingering nearby, their gravity warping these trails? The cartwheel spokes don't just connect its core to its ring, they bridge our understanding to the galaxy's turbulent, unfinished history. Scattered throughout the Cartwheel Galaxy's luminous ring are cosmic powerhouses so intense they outshine entire star clusters, ultra-luminous X-ray sources, or ULXs for short. These brilliant beacons blast out staggering amounts of high-energy X-rays, some shining millions of times brighter than our sun across all wavelengths combined. Normally, X-rays of this magnitude come from material spiraling into supermassive black holes at the centers of galaxies. But here's the catch: these ULXs aren't nestled in the core. They're peppered across the outer ring, defying expectations and leaving scientists scrambling for explanations. So what could possibly fuel such extreme brightness? One leading theory points to intermediate mass black holes, celestial oddities heavier than typical stellar black holes, but lighter than the supermassive giants found in galactic cores. Imagine a black hole weighing anywhere from a few hundred to a few 100,000 times the mass of our sun, devouring gas and dust at a ferocious rate. As material gets superheated on its way into the abyss, it emits those jaw-dropping X-ray flares. The Cartwheel's collision may have birthed these rare objects by flinging smaller black holes into gas-rich regions, feeding them like a cosmic buffet. But there's another contender in this mystery: hyperactive neutron stars. These ultra-dense stellar corpses, no wider than a city yet packing more mass than our sun, aren't normally this luminous. However, if one were spinning at breakneck speeds and wrapped in a powerful magnetic field, it could theoretically siphon material from a nearby star at such an extreme rate that it temporarily outshines physics as we know it. Some ULXs might be these pulsars on steroids, their X-ray beams amplified by conditions we've never observed elsewhere. What makes these sources especially baffling is their refusal to play by the rules. According to conventional physics, there's a limit to how bright an object of a given size can get, the Eddington limit. Yet many of the Cartwheel's ULXs blow past this boundary like it doesn't exist. Some researchers suggest they might be ejecting material in focused jets, redirecting energy in ways that mask their true luminosity. Others propose that their light could be artificially concentrated by reflecting off swirling disks of debris, creating an illusion of impossible brightness. Then there's the eerie spacing of these ULXs clustered in certain parts of the ring but absent in others. Their distribution lines up eerily well with regions where the collision's shockwave compressed gas most violently, hinting that the galaxy's violent reshuffling directly triggered their formation. Whether they're rogue black holes gorging on wreckage or neutron stars pushed to their limits, one thing's certain: these ULXs are rewriting the playbook on how cosmic objects radiate energy. And with each new observation, they nudge us closer to a startling realization that the Cartwheel Galaxy might be hiding an entire zoo of exotic, physics-defying objects in its shimmering ring. Tucked beyond the Cartwheel Galaxy's dazzling blue ring lies a far subtler structure, a whisper-thin halo only visible through infrared eyes. This ghostly outer ring, stretching even farther into the void, glows not with the fierce light of newborn stars but with the gentle warmth of dust grains, heated by ancient starlight to just a few degrees above absolute zero. Unlike its vibrant inner counterpart, this ethereal band doesn't announce itself boldly. Instead, it lingers at the edge of perception, a spectral echo of the galaxy's violent past. What could have sculpted such a faint, sprawling feature? One theory suggests it's a secondary shockwave, the cosmic equivalent of a ripple spreading outward after the initial splash. When the smaller galaxy tore through the Cartwheel's core, the collision might have sent not one but two waves racing outward. The first, more intense surge compressed gas into the brilliant blue ring we see today, while a slower, fainter second wave could have stirred up dust farther out, creating this diffuse infrared glow. Imagine dropping two pebbles into a pond, one large, one small, and watching as their ripples spread at different speeds. The outer ring might be that second, subtler ripple frozen in space. But there's another tantalizing possibility. This could be the remains of the intruder galaxy itself. As the smaller galaxy plowed through the Cartwheel, its stars and gas might have been stretched into a vast, disintegrating stream, some of it flung outward to form this tenuous ring. Infrared observations reveal clumps within the haze, potential remnants of the intruder's original structure, now smeared across hundreds of thousands of light years. If true, this ghostly ring isn't just a byproduct of the collision. It's a cosmic crime scene, the scattered evidence of a smaller galaxy's destruction. The most puzzling clue lies in the ring's temperature. While the inner ring blazes with the heat of young stars, the outer ring's dust is curiously lukewarm. This suggests it isn't actively forming stars, but instead reflects and reprocesses light from the Cartwheel's brighter regions. Some astronomers propose that magnetic fields or sparse gas densities prevent the dust from collapsing into new stars, leaving it to glow passively like embers cooling in a cosmic hearth. Others wonder if the outer ring represents a transitional zone where the galaxy's gravitational grip weakens, allowing dust to spread thin and diffuse, never dense enough to ignite stellar birth. Every observation deepens the intrigue. Recent studies show the outer ring isn't perfectly aligned with the inner one. It wobbles slightly, as if still settling after the collision. This misalignment hints at unseen forces at work, perhaps the gravitational tug of dark matter or lingering turbulence from the impact. And then there's the mystery of why similar rings aren't seen around other collision-reshaped galaxies. Is the Cartwheel's ghostly halo a cosmic rarity, or have we simply not looked hard enough elsewhere? One thing's certain: this faint outer ring is more than just debris. It's a living archive, preserving secrets about the speed, angle, and violence of that ancient galactic crash. By decoding its whispers, we might finally understand not just how the Cartwheel came to be, but how galaxies everywhere transform when forced to collide. And with every new infrared scan, this ghostly structure seems determined to reveal another piece of the puzzle, if only we know how to listen. The Cartwheel Galaxy's outer ring isn't just sprinkled with stars, it's a cosmic wildfire, a storm of stellar birth so intense it defies imagination. Here, stars don't form in quiet nurseries like those in our Milky Way. they erupt in vast cascading waves as if the galaxy itself is caught in a perpetual tsunami of creation. Astronomers call these regions starbursts, but that term barely captures the scale of what's happening. In some pockets of the Cartwheel, new stars ignite hundreds of times faster than anywhere in our home galaxy, turning entire swaths of space into dazzling stellar factories. This frenzy traces back to the galaxy's violent collision. When the smaller galaxy plowed through the Cartwheel's core, it sent shockwaves rippling outward at millions of miles per hour, compressing vast clouds of gas like an invisible hand crumpling paper. Where these shockwaves passed, gas reached critical density, collapsing under its own weight into searing protostars. Imagine a snowball rolling downhill, gathering mass until it becomes an avalanche, except here, the avalanche is made of hydrogen and helium, and it's birthing thousands of stars at once. What's left behind isn't a neat, orderly cluster, but a chaotic sprawl of blue supergiants, their collective light so bright it drowns out older stars nearby. But the real spectacle lies in how these starbursts move. Unlike static star clusters, some regions appear to surf along the ring, their wave-like motion frozen in time. One theory suggests this illusion comes from the collision's shockwave still propagating outward, triggering star formation sequentially like dominoes falling in slow motion. As the wavefront travels, it leaves behind pockets of newborn stars, creating the impression of a stellar tide rolling through the galaxy, another possibility. The ring's rotation might be distorting our view, with faster-moving sections of gas igniting stars earlier, creating a staggered effect that mimics motion. Even more bizarre are the orphan clusters, groups of young stars drifting ahead of the main wave, seemingly out of sync with the rest. These outliers might be evidence of turbulence within the ring, where denser gas clumps collapsed independently, or perhaps they're the remnants of smaller shockwaves bouncing back inward like echoes. Whatever the cause, their presence hints that the Cartwheel star-forming machinery is far messier and more fascinating than we ever predicted. What's clear is that this galaxy isn't just forming stars differently, it's rewriting the rules. Normally, stellar nurseries rely on slow, gravity-driven collapse. Here, the process is explosive, urgent, as if the galaxy is racing against time to rebuild itself after catastrophe. The result is a celestial laboratory unlike any other, where we can witness the extremes of star birth firsthand. And with every new observation, the Cartwheel's stellar tsunamis remind us, in the aftermath of chaos, creation can be just as breathtaking as destruction. Hidden within the Cartwheel Galaxy's mesmerizing structure lies a cosmic ghost story, an absence so profound it challenges our understanding of how galaxies hold themselves together. This galaxy seems to be missing something invisible yet essential: dark matter. Current observations suggest the Cartwheel contains far less of this mysterious substance than predicted, leaving astronomers scratching their heads. Dark matter is the hidden scaffolding of the universe, the unseen glue that keeps galaxies from flying apart. Without enough of it, the Cartwheel's very existence defies conventional models of galactic evolution. So where did it go? One compelling theory points to the galaxy's violent collision as the culprit. When the smaller intruder galaxy slammed through the Cartwheel's core, the gravitational chaos might have ripped away vast amounts of dark matter, scattering it into intergalactic space like smoke dispersing in the wind. Picture two clouds of dark matter, one from each galaxy passing through each other during the collision. Unlike stars and gas, which collide and interact, dark matter barely notices ordinary matter. It could have simply kept moving, carrying its gravitational influence away from the Cartwheel's core and into the void beyond, but not everyone's convinced. Some researchers argue the missing dark matter might be an illusion, a trick of measurement. The Cartwheel's peculiar shape makes it notoriously difficult to study. Its stars and gas move in complex, turbulent patterns, tangled by the collision's aftermath. Traditional methods of estimating dark matter, like tracking stellar velocities or gravitational lensing, become muddled in such a chaotic environment. What if we're not seeing a true deficit, but rather struggling to interpret the data correctly? Alternatively, the dark matter might still be there, just redistributed in ways we don't yet recognize, perhaps stretched into a diffuse halo too faint to detect with current technology. The implications are staggering. If the Cartwheel genuinely lost dark matter during the collision, it could rewrite theories about how galaxies survive such encounters. Most models assume dark matter acts as a stabilizing force, anchoring galaxies even as visible matter gets reshuffled. But if a collision can strip it away, that might explain why ring galaxies like the Cartwheel are so rare. Perhaps most galaxies lacking sufficient dark matter after a crash simply disintegrate. On the other hand, if our measurements are flawed, it hints at deeper gaps in our understanding of how dark matter interacts with the visible universe. This puzzle extends far beyond one galaxy. The Cartwheel's missing dark matter could hold clues about the nature of this elusive substance itself. Is dark matter sticky in ways we haven't accounted for? Could it clump differently in collision-ravaged galaxies than in pristine ones? Every new observation peels back another layer of the mystery, reminding us that even the most fundamental building blocks of the cosmos still defy easy explanation. And until we solve it, the Cartwheel Galaxy remains not just a marvel to behold, but a cosmic riddle waiting to be decoded. Deep within the Cartwheel Galaxy's ancient core, something isn't sitting still. The supermassive black hole that should anchor everything appears to be on the move. Most galaxies have their central black holes firmly rooted at the gravitational heart, like a spider at the center of a web. But recent observations suggest this one might be wobbling, its position subtly shifting as if still reeling from the galaxy's catastrophic collision millions of years ago. This cosmic heavyweight, typically millions of times more massive than our Sun, doesn't just drift without consequence. If it's truly displaced, the implications could reshape our understanding of how black holes behave after galactic crashes. One possibility is that the smaller intruder galaxy's passage delivered such a violent gravitational kick that it knocked the black hole off balance, sending it oscillating through the core like a pendulum in slow motion. Picture two wrestlers grappling. The smaller one might not win, but they could still throw their opponent off-center. In this case, the wrestlers were entire galaxies, and their clash left the black hole staggering through a cloud of stars. Another theory suggests the black hole might not be alone. Some models propose the collision could have delivered a second, smaller black hole, the former heart of the intruder galaxy, now locked in a slow dance with the primary one. Their gravitational tug-of-war would create complex wobbles in the core, distorting the paths of nearby stars and gas. Astronomers are hunting for telltale signs of this cosmic pas-de-deux, like stars abruptly changing speed or gas clouds swirling in unexpected patterns around the core. The most startling possibility, the black hole might be in the process of being ejected entirely. Galactic collisions can act like gravitational slingshots, flinging black holes outward at incredible speeds. While it's unlikely the Cartwheel's black hole would escape completely, it's simply too massive. Even a partial displacement could have dramatic effects. A wandering supermassive black hole would drag clusters of stars with it, creating a trailing wake of stellar disruption. Over time, this could leave the galaxy's core strangely diffuse, lacking the dense star clusters typically found around central black holes. What makes this wobble so critical to study isn't just the spectacle, it's the window into how black holes influence their galaxies. Normally, these cosmic giants regulate star formation by heating surrounding gas with powerful jets. But a displaced black hole might spew energy in unpredictable directions, potentially igniting or quenching star formation in uneven bursts across the galaxy. Some researchers speculate this could explain why the Cartwheel's core shows such suppressed stellar birth compared to its vibrant outer ring. Every wobble tells a story. By tracking the black hole's motion if confirmed, we might reconstruct the collision's precise angle and energy. Its current path could reveal whether the intruder galaxy came in fast and shallow or slow and steep, offering clues about the Cartwheel's transformation. And if there really is a second black hole lurking nearby, their eventual merger would unleash gravitational waves powerful enough to ripple across the universe. Until then, this celestial heavyweight's unsteady dance remains one of the galaxy's most compelling mysteries, proving that even the mightiest objects in the cosmos aren't immune to being knocked off their feet. Most galaxies have magnetic fields that flow in smooth, orderly patterns like the spiraling grooves of a vinyl record. But the Cartwheel Galaxy, its magnetic field looks like it's been put through a cosmic blender, twisted, tangled, and utterly chaotic. Radio telescope observations paint a picture of invisible forces in turmoil, with magnetic lines looping and knotted in ways never seen in a typical spiral galaxy. This isn't just a random mess, it's a direct consequence of the collision that reshaped the Cartwheel, a lingering fingerprint of violence written across the fabric of space itself. What makes this magnetic mayhem so unusual is how it defies the norm. In undisturbed galaxies, magnetic fields align with the spiral arms, gently guiding gas clouds and influencing star formation like invisible cosmic rails. Here, the field lines are shredded, their usual coherence destroyed by the collision's shock waves. Imagine tossing a handful of iron filings onto a shaken sheet of paper, their usual neat patterns dissolve into chaos. That's essentially what happened to the Cartwheel's magnetic architecture when another galaxy plowed through it. The resulting turbulence didn't just scramble stars and gas, it turned the galaxy's entire electromagnetic scaffolding into a cosmic knot. But here's where it gets even stranger. This disordered magnetic field isn't just a curiosity, it's actively shaping the galaxy's evolution. In common galaxies, magnetic fields help regulate star birth by preventing gas clouds from collapsing too quickly. In the Cartwheel, the opposite might be happening. The field's twisted strands could be creating pockets of intense pressure, squeezing gas into star-forming frenzy in some regions while stifling it in others. This could explain why the galaxy's starbursts appear in erratic clusters rather than evenly distributed waves. The magnetic chaos might also be accelerating cosmic rays to extraordinary energies, flinging high-energy particles across interstellar space like a malfunctioning particle accelerator. The most baffling aspect, despite the turmoil, some areas show surprising magnetic coherence filaments that somehow resisted the collision's chaos. These resilient threads, detected threading through the outer ring, hint that magnetic fields might have a kind of memory, retaining traces of their original structure even after catastrophic disruption. One theory suggests they're anchored by dense clumps of matter that survived the collision, acting like buoys in a stormy sea, keeping fragments of order intact. Understanding this magnetic pandemonium isn't just about solving one galaxy's mysteries. It challenges fundamental assumptions about how magnetic fields behave under extreme conditions. If the Cartwheel's mangled field can persist for millions of years, does that mean other colliding galaxies hide similar electromagnetic chaos? Could these turbulent fields seed even more exotic phenomena like hypercharged particle jets or bizarre plasma vortices? Every new radio observation peels back another layer, revealing a hidden dimension of the Cartwheel story, one written not in light but in the silent, twisting language of magnetism. Every cosmic collision leaves a culprit, but in the Cartwheel Galaxy's case, the perpetrator seems to have vanished without a trace. Astronomers call it the Phantom Companion, the smaller galaxy that barreled through the Cartwheel's core millions of years ago, triggering its dazzling ring formation. Yet despite decades of searching, this galactic intruder remains frustratingly elusive. Where did it go? And if it's truly gone, why does the Cartwheel still behave as if something unseen is tugging at its edges? The Phantom Companion's absence is more than just a celestial whodunit, it's a genuine puzzle. When galaxies collide, they rarely escape unscathed. Even if the smaller one is torn apart, its stars and dark matter should linger as a smeared trail or a distorted halo. But searches for such debris around the Cartwheel have turned up empty-handed. Some researchers propose the intruder might have been a rare breed, a dark galaxy, composed mostly of invisible matter with few stars to betray its presence. If true, the collision could have scattered its dark matter into an undetectable haze, leaving behind only gravitational ripples as evidence. Others suggest an even wilder possibility. The companion might not have been a galaxy at all, but a massive, starless cloud of gas. Picture a cosmic iceberg, mostly hydrogen, invisible in optical light plowing through the Cartwheel's core. The collision's shock waves would still compress the Cartwheel's gas into that iconic ring, but without stars or dark matter to trace, the intruder could evaporate into the void, leaving no identifiable wreckage. Yet hints of the phantom's presence persist. The Cartwheel's outer ring wobbles slightly, as if tugged by an unseen mass. Some of its star clusters orbit at odd angles, suggesting they're responding to gravitational influences beyond what visible matter can explain. Could remnants of the companion still lurk in the darkness, camouflaged by distance or tangled magnetic fields? Or perhaps the collision slingshotted the intruder away at incredible speed, flinging it beyond current detection limits, a cosmic bullet lost in the vastness of intergalactic space. The most tantalizing clue comes from an unusual stream of hydrogen gas drifting near the Cartwheel's outskirts. This faint ribbon, detected only in radio wavelengths, curves in a way that mirrors the expected path of a fleeing galaxy. If confirmed as the Phantom's last gasp, it could finally solve the mystery, revealing not just where the intruder went, but how such collisions redistribute matter across the universe. Until then, the Cartwheel keeps its secrets, a celestial detective story with no final chapter, and for astronomers, that's what makes it irresistible. Every unexplained wobble, every odd star cluster whispers the same question: is the phantom companion truly gone, or is it hiding in plain sight, shaping the galaxy from the shadows? One side of the Cartwheel Galaxy's dazzling ring burns brighter than the other, a celestial lopsidedness so striking it looks almost unfinished. While the entire structure glows with newborn stars, the southwest region blazes with ultraviolet and X-ray light at intensities that dwarf the rest of the ring. This asymmetry isn't a trick of perspective or a camera artifact. It's a real physical imbalance, a clue written in radiation about the forces shaping this galactic spectacle. The leading theory points back to the original collision's violence. When the smaller galaxy tore through the Cartwheel's core, it didn't strike a perfectly centered blow. Instead, it likely hit at an angle, delivering more energy to one side than the other. Picture a hammer smashing into a spinning wheel. The side that took the direct hit would deform more drastically, while the opposite side might ripple more gently. In the Cartwheel's case, that uneven impact sent stronger shock waves surging through the southwestern gas clouds, compressing them into denser, hotter knots where star formation ignited like a chain reaction. The result, a stellar baby boom of epic proportions, with massive blue stars burning ferociously and spewing X-rays as their stellar winds collide. But shockwaves alone might not tell the whole story. Another possibility lies in the ring's own chaotic composition. Gas density in the Cartwheel isn't uniform. Some regions are thicker, packed with more raw material for star formation, while others are sparse. The brighter side might simply be where the shockwave plowed into a pre-existing gas reservoir, a cosmic lightning strike hitting fuel-rich ground. Meanwhile, the dimmer side could represent where the wave encountered thinner material, leaving fewer stellar embers in its wake. Then there's the wild card, feedback from massive stars themselves. In the brightest regions, the first generation of stars might have already lived and died in spectacular supernovae, their explosions heating surrounding gas and triggering secondary waves of starbirth. This self-reinforcing cycle could create pockets of hyperactivity, like wildfires spreading faster where the wind blows strongest. Meanwhile, other parts of the ring might still be in the calm before the storm, their stellar factories just warming up. The asymmetry could also hint at something deeper, an unseen gravitational tug. Some astronomers speculate that remnants of the intruder galaxy, or even a hidden dark matter clump, might be warping the ring's structure from afar, subtly steering gas flows toward one side. Others suggest magnetic fields scrambled by the collision could be channeling energy unevenly, turning parts of the ring into particle accelerators while leaving others relatively quiet. What makes this lopsided glow truly fascinating is how it defies expectations. Most models of galactic collisions predict roughly symmetrical results, yet nature, as usual, prefers complexity. By studying these imbalances, astronomers aren't just solving a local mystery, they're learning how chaos translates into patterns across the universe. And with every new telescope scan, the cartwheel's brighter half seems to whisper the same tantalizing question. In a cosmos built on symmetry, why does asymmetry so often steal the show? Nestled within the Cartwheel Galaxy's luminous ring are stellar cities so packed they make downtown Manhattan look spacious, superstar clusters crammed with hundreds of thousands of stars in regions barely wider than our solar system. These cosmic metropolises glow with the combined light of millions of suns, their density so extreme that if you stood on a planet inside one, the night sky would blaze with stars brighter than a full moon. Yet what's truly baffling isn't just their crowded conditions, it's how they even exist at all. Normal star clusters form when gas clouds collapse, but they rarely reach such bewildering densities without flying apart. The Cartwheel's clusters, however, were forged in the furnace of its galactic collision. When the shock wave from the impact plowed through the galaxy's gas, it didn't just compress material, it crushed it, triggering runaway star formation in hyper-concentrated pockets. Imagine a snow globe shaken with such force that the flakes fuse into solid clumps, except here the flakes are stars, and the shaking was a galaxy-sized cataclysm. The result, clusters so massive and dense they straddle the line between conventional star groups and the universe's oldest stellar relics, globular clusters. This raises a tantalizing question: are we witnessing the birth of globular clusters, those ancient, gravitationally bound stellar swarms that orbit most galaxies? Typically, globular clusters formed billions of years ago, their origins lost in the early universe's chaos. But the Cartwheel's superclusters offer a rare glimpse into how such structures might emerge today. Some models suggest these young giants could indeed evolve into globulars, given enough time to stabilize. Others argue their frenzied birth might doom them. Their stars packed so tightly that gravitational interactions will eventually fling most of them outward, leaving behind only a sparse core. Then there's the mystery of the runaway clusters. Several of these stellar megacities appear to be hurtling away from the ring at speeds that defy easy explanation. One culprit could be asymmetric supernova explosions. If enough massive stars in a cluster's core detonate on one side, the collective kickback might propel the entire structure like a cosmic rocket. Another possibility involves gravitational slingshots. Perhaps the clusters sailed too close to dense gas clouds or hidden black holes, getting whipped into motion by unseen forces. The most intriguing outliers are those moving almost perpendicular to the ring, as if ejected by some violent event. Could these be evidence of a secondary collision, or the gravitational fingerprint of the still missing intruder galaxy? Every fleeing cluster holds clues, its trajectory a breadcrumb trail pointing back to the Cartwheel's tumultuous past. And with each new observation, these overcrowded stellar cities challenge our assumptions, not just about how stars gather, but how the universe builds its most enduring structures from chaos. When astronomers tuned their radio telescopes toward the Cartwheel Galaxy, they expected to hear the usual chorus of stellar activity, but instead they picked up something far stranger. Faint radio waves ripple across the galaxy's outer edges, not quite matching the positions of its brightest visible features. these delayed signals arrive like cosmic echoes, lagging behind the light of newborn stars by thousands of years. It's as if the galaxy is whispering its history in two different languages, one immediate and blazing, the other slow and lingering. One explanation points to the ghosts of dead stars. When massive stars in the Cartwheel's ring explode as supernova, their violent death sends shockwaves plowing through surrounding gas at breakneck speeds. These shocks can persist for millennia, accelerating electrons to near light speeds and generating synchrotron radiation, the same process that powers pulsars and quasars. The catch, while the supernova's visible flash fades in weeks, its radio aftermath lingers, glowing faintly as the shockwave gradually dissipates. The Cartwheel's starburst rings are essentially supernova graveyards, their delayed radio signatures tracing where stars died long after their light has vanished from view. But there's another layer to the mystery. Some of these radio echoes don't align with any known stellar remnants. Instead, they hover in seemingly empty patches of intergalactic space, faint but persistent. One theory suggests they're traces of the collision itself, ripples in the galaxy's magnetic field that were stretched and twisted during the impact, like invisible scars finally revealing themselves. As these distorted fields slowly relax, they could be emitting low-frequency radio waves, a calming sigh after the cosmic violence that reshaped the galaxy. The most tantalizing possibility involves an intergalactic shroud. The Cartwheel might be plowing through a diffuse cloud of gas too thin to see in optical telescopes but dense enough to interact with its magnetic field. As charged particles in this haze collide with the galaxy's outer layers, they could generate radio static, a faint hiss marking where the Cartwheel brushes against the void. If true, these echoes would map not just the galaxy's internal drama, but its ongoing dance with the invisible currents of intergalactic space. What makes these radio whispers so compelling is their defiance of time. While light shows us the Cartwheel as it was millions of years ago, its radio echoes reveal processes unfolding across vastly different timescales, some instantaneous, others achingly slow. Together, they paint a portrait of a galaxy still reverberating from ancient trauma, its story told in wavelengths visible only to those patient enough to listen. And with every new observation, the Cartwheel proves that even in silence, it has volumes left to say. The Cartwheel Galaxy isn't just divided by age and structure, it's split by chemistry. While most galaxies show a gradual gradient of heavy elements with richer concentrations toward their cores, this cosmic oddball flips the script entirely. Its vibrant outer ring gleams with an abundance of metals astronomers speak for elements heavier than hydrogen and helium, while its central bulge remains strikingly impoverished, like a donut dusted with gold but hollow at the center. This inverted metallicity map isn't just unusual, it's a glaring clue about how galactic collisions can scramble a galaxy's very DNA. So how did this cosmic alchemy unfold? The answer lies in the collision's aftermath. When the smaller galaxy punched through the Cartwheel's core, it didn't just rearrange stars, it flung the galaxy's heavy elements outward like a chef tossing salt over their shoulder. Massive stars in the original disk, forged in earlier epochs of star formation, had spent their lives cooking metals in their cores before exploding as supernova, seeding their surroundings with elements like oxygen, carbon, and iron. Normally, these metals would sink toward the galactic center over time, drawn by gravity, but the collision's shock waves acted like a cosmic blender, churning the galaxy's guts and propelling enriched gas outward into the ring, where it fueled new generations of metal-rich stars. Meanwhile, the core tells a story of loss. Stripped of much of its gas by the collision, the central bulge was left starved of the raw materials needed to forge fresh metals. Older stars there continue to burn, but without younger, metal-packed replacements, the region's overall metallicity stagnates. It's as if the galaxy's heart was frozen in time, its chemistry locked in a state predating the catastrophic encounter. But here's where things get even stranger. Certain patches of the ring defy expectations, showing bizarrely low metallicity despite the surrounding abundance. These metal deserts might be windows into the intruder galaxy itself, regions where its pristine, metal-poor gas mixed with the Cartwheel's enriched material but didn't fully homogenize. Imagine pouring cream into coffee and finding stubborn streaks that refuse to blend. These pockets could be the cosmic equivalent, preserving the intruder's original composition like fossils in amber. The implications ripple far beyond one galaxy. If collisions can violently redistribute elements this way, it might explain why some galaxies in the early universe, seen as they were just after chaotic formative collisions, show erratic metallicity patterns. The Cartwheel could be a local time machine, showing us how the cosmos recycled its building blocks in the turbulent past. And with every new spectral analysis, this lopsided chemical map poses sharper questions. How long until the core catches up? Will metals eventually migrate back inward, or is the galaxy forever fractured into rich and poor halves? The Cartwheel's silent elemental divide holds answers not just about its own history, but about how the universe itself grows richer, one catastrophic encounter at a time. At the Cartwheel Galaxy's heart, something isn't just active, it's unpredictable. The core flickers like a cosmic candle, its brightness surging and fading in irregular bursts that defy the steady rhythms of most supermassive black holes. Some days, if days existed on galactic timescales, it shines with the intensity of a quasar, flooding its surroundings with high-energy X-rays. Other times, it dims to a whisper, as if the engine driving it has momentarily stalled. These aren't the gentle pulsations of a well-fed black hole. They're erratic, almost frantic, as if the galaxy's core is trapped in a cycle of cosmic indigestion. What could cause such instability? One explanation lies in the chaos of the collision. When the smaller galaxy plowed through the Cartwheel's center, it didn't just disrupt stars, it hurled vast amounts of gas toward the central black hole in erratic, clumpy waves. Normally, black holes feed from smooth, orderly accretion disks like water spiraling down a drain. But here, the disk might be fragmented, a mess of swirling debris where gas piles up unevenly before crashing inward in fits and starts. Picture trying to drink from a hose that keeps kinking and unkinking. You'd get gulps instead of a steady flow. That's likely what's happening in the Cartwheel's core, with each gulp of gas igniting a fresh outburst of energy. Then there's the possibility of echoes. Some of the flickering might not be real-time activity at all, but light from past flares bouncing off clouds of dust and gas lingering near the core. Imagine shouting in a cavern. The sound doesn't just come straight back. It reverberates, arriving at your ears from multiple angles at different times. Similarly, X-rays from an ancient flare could be ricocheting through the galaxy's wreckage, creating the illusion of fresh bursts long after the original event faded. The most tantalizing theory involves a binary black hole. Could the collision have left the Cartwheel's original supermassive black hole paired with a smaller one, the intruder galaxy's former anchor, locked in a lopsided dance? As the two orbit each other, their gravitational tugs might disrupt the flow of gas, alternately feeding and starving the primary black hole in cycles of feasting and famine. Each close pass could trigger a new flare, like a pendulum swinging too close to a flame. What makes these flickers so fascinating isn't just their cause, it's their effect. Most active galactic nuclei regulate their host galaxies like a thermostat, their energy output shaping star formation rates across vast distances. But the Cartwheel's core behaves more like a malfunctioning switch, its sporadic outbursts potentially creating pockets of turbulence where stars form in fits and starts. Some regions of the outer ring might owe their starbursts not just to the original collision, but to these delayed, unpredictable surges from the center. Every flicker is a clue. By untangling their rhythms, astronomers could reconstruct the collision's aftermath in unprecedented detail. not just the broad strokes, but the fine print of how galaxies heal or fail to after catastrophic encounters. And until then, the Cartwheel's restless core keeps sending its cryptic Morse code across the cosmos, a reminder that even the mightiest objects in the universe sometimes struggle to find their balance. The Cartwheel Galaxy isn't alone in its cosmic dance. It's surrounded by a troop of tiny companion galaxies whirling around it in dizzying, unpredictable patterns. These dwarf satellites, some no larger than star clusters, don't follow the orderly orbits seen around most large galaxies. Instead, they dart and loop like drunken fireflies, their paths so erratic they've left astronomers questioning everything we thought we knew about galactic gravity. One of these dwarfs, nicknamed the Skipper, races along an elongated orbit that takes it soaring far beyond the Cartwheel's main disk before plunging back inward at a steep angle. Another, the Waver, seems to hesitate mid-orbit, as if encountering invisible speed bumps in space. Their odd motions suggest one of two possibilities. Either these dwarfs were born alongside the Cartwheel and had their orbits scrambled by the collision, or they're interlopers, captured during the catastrophic event and still reeling from the gravitational upheaval. The captured galaxy theory holds particular intrigue. If these dwarfs were once independent, their chaotic paths might preserve clues about the collision's trajectory. Imagine throwing a handful of marbles into a spinning dish. The way they scatter could reveal the angle and force of the toss. Similarly, the dwarfs' wild orbits might trace the intruder galaxy's original path through the Cartwheel. Some models even suggest one of these tiny galaxies could be a surviving fragment of the intruder itself, a piece torn loose during the impact and now trapped in a gravitational tug-of-war. But there's a twist. Some of these dwarfs are unusually rich in heavy elements for their size, a trait more typical of galaxies that formed in densely populated regions rather than isolated ones like the Cartwheel. This chemical fingerprint raises the possibility they're not native to this cosmic neighborhood at all, but strays drawn in from passing galaxy groups, their orbits further destabilized by the collision's lingering shockwaves. The most puzzling outlier is a dwarf that appears to be moving against the Cartwheel's rotation, like a salmon swimming upstream. Such retrograde motion is rare in satellite galaxies and usually points to a violent capture history. If confirmed, this rebellious companion could be the smoking gun proving the Cartwheel's collision was even messier than we thought, with enough gravitational chaos to flip an entire galaxy's orbit. What's clear is that these dancing dwarfs are more than just celestial curiosities. They're living records of the Cartwheel's turbulent past. By decoding their motions, we might finally reconstruct the exact sequence of events that birthed this cosmic oddity. And until then, their erratic pirouettes serve as a reminder, even on galactic scales, gravity doesn't always play by the rules. While the Cartwheel Galaxy dazzles our eyes with its brilliant blue ring and golden core, there's an entire hidden dimension to this cosmic spectacle, one that only reveals itself in the faint whisper of infrared light. Beyond the galaxy's visible edges, an enormous, ghostly halo glows with the warmth of dust so cold it's nearly frozen, stretching hundreds of thousands of light years into the void. This isn't just scattered debris, it's a cryptic envelope of material that defies simple explanations, hinting at processes we've only begun to unravel. What makes this infrared glow so puzzling is its sheer scale. Most galaxies have some dust lingering around them, but the Cartwheel's halo is colossal, far larger than models predict for a ring galaxy of its age. Some of this dust is undoubtedly debris from the collision, flung outward by the impact like cosmic shrapnel, yet its temperature tells a stranger story. Unlike the warmer dust in the star-forming ring, this outer material hovers just a few degrees above absolute zero, barely radiating any heat at all. That suggests it's not being actively warmed by stars, but instead reflects or reprocesses light from the galaxy's brighter regions, like a distant mirror catching the last embers of a fire. But cold dust alone doesn't explain everything. Parts of the halo flicker with sporadic warmth pockets where hidden star formation might be occurring in total secrecy. In these shadowy regions, gas could be collapsing into stars obscured by so much dust that not even infrared telescopes fully pierce the veil. These stealthy stellar nurseries would challenge our assumptions about where and how stars can form, proving that galactic collisions don't just ignite fireworks in their main rings but also spark hidden flames in their farthest outskirts. Then there's the dark matter angle. Could this halo's unusual structure, its uneven glow, its faint tendrils reaching into intergalactic space, be shaped by invisible matter's gravitational pull? Dark matter doesn't emit or absorb light, but its presence can herd dust into unexpected configurations, leaving subtle fingerprints in the infrared haze. If so, studying this halo might offer one of the clearest maps yet of how dark matter is distributed around a collided galaxy, a cosmic X-ray revealing the unseen scaffolding beneath the beauty. The most tantalizing possibility, this halo might not belong to the Cartwheel alone. Some astronomers speculated could be the remnants of the intruder galaxy, not just its scattered stars, but its entire reservoir of cold, primordial dust stretched into a diaphanous shroud by the collision's gravitational tides. If true, the halo is more than a byproduct. It's the ghost of a galaxy, its essence lingering long after its structure was dissolved. Every new infrared observation peels back another layer of the mystery. From stealthy star formation to dark matter's invisible hand, this faint glow is a cosmic palimpsest, written and rewritten by forces we're only beginning to decipher. And as long as it flickers in the darkness, the Cartwheel Galaxy will keep challenging us to look beyond what's visible, to seek the stories hidden in the cold and the quiet. Even in a galaxy as bizarre as the Cartwheel, some features stand out as true cosmic rebels, vast clouds of gas spinning stubbornly backward, defying the galaxy's dominant rotation like salmon swimming upstream. These rogue clouds aren't just quirky exceptions, they're smoking guns from the collision that reshaped this galaxy. Their reversed motion a direct consequence of the chaos unleashed when another galaxy plowed through its heart. Imagine a whirlpool suddenly struck by a passing ship. The water's smooth spiral would erupt into turbulence, with eddies spinning every which way. That's essentially what happened to the Cartwheel's gas during the collision. Shockwaves from the impact didn't just compress material outward. They sent some clouds careening in entirely new directions, their angular momentum flipped by gravitational slingshots. Some of these maverick clouds might have been wrenched backward as the smaller galaxy grazed past, its gravity tugging them into retrograde motion. Others could be fragments of the intruder itself, carrying their original spin into a new galactic home. The implications go far beyond celestial acrobatics. Gas rotation governs how and where stars form, so these backward spinning pockets could become nurseries for stellar oddities. Normally, stars inherit their motion from the gas clouds that birthed them, orbiting harmoniously with their galactic neighborhood. But stars born in these rebellious clouds might revolve against the galactic flow, destined to crash into neighboring systems like wrong-way drivers on a cosmic highway. Some astronomers suspect this chaos could forge hypervelocity stars, objects flung outward at breakneck speeds when stellar orbits intersect catastrophically. Others theorize that retrograde gas might suppress star formation entirely, its counterflow creating turbulence too intense for stable stellar birth. Either way, these rogue clouds aren't just relics of the past, they're time bombs of future instability. Their backward spin a reminder that the collision's disruption will echo for eons. Most intriguing are the clouds caught mid-reversal, their outer layers spinning one way while their cores twist the opposite direction. These cosmic tug-of-wars reveal gas dynamics in extreme environments, offering glimpses of how angular momentum gets redistributed after galactic trauma. By studying them, we might finally understand why some collided galaxies eventually settle into order while others, like the Cartwheel, remain gloriously unbalanced. One thing's certain, these backward whirlpools prove that even in a universe governed by symmetry, collisions can rewrite the rules, leaving behind pockets of beautiful defiance. And as long as they spin against the tide, they'll challenge our assumptions about how galaxies heal, evolve, and occasionally refuse to conform. Among the Cartwheel Galaxy's many enigmas, few are as energetically baffling as its gamma-ray hotspots, regions where space itself seems to crackle with the universe's most potent photons. These concentrated bursts of high-energy radiation flicker unpredictably across the galaxy's outer ring, defying straightforward explanation. Gamma rays don't just signify cosmic violence, they're the universe's emergency flares, signals of particle acceleration at the extreme edges of physics. Yet here they cluster in patches with no visible engines, no supernova remnants, no pulsars, no obvious black hole jets. It's like finding a spotlight in a dark room with no bulb. One leading suspect, supernova on steroids. When ultramassive stars collapse, they can unleash explosions 100 times more energetic than typical supernova, creating shockwaves potent enough to accelerate particles to near light speeds. The resulting gamma-ray bursts are brief but spectacular, like cosmic flashbulbs. If the Cartwheel starburst ring birthed such monsters, their afterglow could explain some hotspots. Yet hypernova are rare, and their gamma signatures usually fade within weeks. The persistence of these emissions suggests something more sustained, as if the galaxy has tapped into a hidden power source. Then there's the dark matter angle. Though invisible, this mysterious substance might decay or collide in ways that release gamma photons. If dark matter clusters unevenly in the Cartwheel's wreckage, perhaps pooled by the collision's gravitational turbulence, its decay could ignite these eerie beacons. Imagine invisible matter slowly unraveling, its energy emerging as light only in these isolated pockets. While speculative, the idea gains traction because the hotspots don't always align with visible structures, as if something unseen is broadcasting from the shadows. A wilder possibility involves the galaxy's mangled magnetic fields. Turbulence from the collision could have twisted these fields into natural particle accelerators, far more efficient than anything on Earth. Charged particles caught in these electromagnetic whirlpools might spiral to insane energies before colliding to produce gamma rays. It's akin to a cosmic version of the Large Hadron Collider, but with no off switch, just a relentless, invisible machine scattering high-energy photons across the void. What's unnerving is the lack of a smoking gun. Normally, gamma rays come packaged with other clues: X-rays, radio waves, or telltale stellar wreckage. Here, the emissions stand oddly alone, like a scream with no echo. Could we be seeing the aftermath of exotic physics, black hole mergers, quark nova eruptions, or even defects in spacetime itself? Or perhaps the Cartwheel's collision forged something entirely new, a particle accelerating mechanism we've yet to theorize. Every flicker from these hotspots is a challenge thrown at our understanding of cosmic energy. They remind us that the universe, even in chaos, hides patterns we're only beginning to trace. And until we crack their code, the Cartwheel's gamma-ray mysteries will keep shining brilliant, baffling, and utterly defiant. Time seems to move differently in the Cartwheel Galaxy, not just in the cosmic sense, but in the way whole regions appear frozen mid-transformation, as if the collision pressed pause on its evolution. While most galaxies reshaped by such violent encounters eventually settle into new equilibrium, whether as spirals, ellipticals, or irregular blobs, the Cartwheel lingers in a state of arrested development. Its brilliant outer ring hasn't diffused, its lopsided structure hasn't evened out, and its chaotic magnetic fields still crackle with unrest. This isn't just a slow recovery, it's like watching a movie stuck on the same frame, leaving astronomers to question what invisible forces are keeping this galaxy trapped in its post-crash splendor. One theory blames isolation. The Cartwheel floats in a relatively empty pocket of space, far from the dense galaxy clusters where gravitational interactions might jostle it into motion. Without neighboring galaxies to tug on its gas or stir its stars, the system could be evolving in slow motion, like a wound that won't heal without air. In crowded galactic neighborhoods, frequent flybys act like physical therapy, keeping gas clouds churning and preventing structures from stagnating. But here, the Cartwheel's drama unfolded in cosmic solitude, leaving its wreckage to cool and settle at a glacial pace. Yet environment alone doesn't explain everything. The galaxy's own internal dynamics might be working against it. Take the outer ring. Normally, shockwaves from a collision dissipate within a few 100 million years, allowing gas to regroup and stars to spread evenly. But the Cartwheel's ring persists, possibly because its magnetic fields, twisted into cosmic knots during the impact, are acting like a cage, trapping gas in place. Imagine a snow globe that never settles because someone keeps shaking it from within. Magnetic turbulence could be that unseen hand, sustaining the chaos long after the initial crash. Then there's the dark matter mystery. If the collision really did strip away much of the Cartwheel's dark halo, as some observations suggest, the galaxy might lack the gravitational scaffolding needed to reorganize itself. Dark matter doesn't just glue galaxies together, it guides their long-term architecture. Without enough of it, the Cartwheel could be like a building with half its framework removed, unable to fully rebuild. The most tantalizing clue comes from the galaxy's star formation rates. While the outer ring blazes with newborn stars, the inner regions are eerily quiet, too quiet. This imbalance suggests the Cartwheel isn't just frozen, it's stuck in a feedback loop. The ring's starbursts eject gas outward, starving the core of fuel for future star birth. Without fresh stars to heat and mix the core's remaining gas, the region grows stagnant, which in turn prevents the galaxy from redistributing mass and evening out. It's a cosmic catch-22, where the very process that makes the Cartwheel so dazzling might also be keeping it trapped in limbo. What's clear is that this isn't just a snapshot of a galaxy mid-recovery. It's a challenge to our assumptions about how galaxies heal. Maybe some cosmic wounds leave permanent scars, or perhaps we're witnessing a new kind of galactic life cycle, one where collisions don't just reshape galaxies but redefine their very futures. Either way, the Cartwheel's frozen evolution reminds us that in the universe, even chaos can become a kind of order, if you wait long enough. The Cartwheel Galaxy's outer ring is a celestial fireworks display, a breeding ground for massive stars that should, by all accounts, explode in brilliant supernova on cosmic schedules. Yet astronomers face a glaring contradiction. Despite the ring's frenzied star formation, confirmed supernova sightings here are vanishingly rare. It's as if the galaxy is producing stellar giants only for them to disappear without a bang, leaving behind a cosmic detective story with no obvious culprit. One explanation lurks in the shadows, literally. The Cartwheel's ring is choked with dust, remnants of the collision that birthed it. These microscopic particles could be acting like a cosmic smokescreen, absorbing the light of supernova before it reaches our telescopes. Imagine a firework bursting behind thick fog. The silhouette might be visible, but the full spectacle remains hidden. Similarly, if supernova ignite deep within dust clouds, their visible light could be smothered, leaving only faint infrared echoes detectable by specialized instruments. Some researchers argue we're simply missing the show, our view obstructed by the very debris that makes the Cartwheel so dazzling in other ways. But dust might not tell the whole story. The galaxy's extreme environment could be breeding stars that defy conventional life cycles. In the Cartwheel's turbulent ring, stellar nurseries operate under pressures rarely seen elsewhere, potentially creating supermassive stars that collapse directly into black holes without the classic supernova finale. Think of a building imploding rather than exploding, no fiery blast, just a silent descent into darkness. If these failed supernova dominate, the galaxy's death toll would be high, but the evidence scant. Supporting this, some models suggest that metal-rich gas in the ring, a byproduct of earlier star deaths, might alter how stars age, pushing them toward quieter fates. Then there's the timing dilemma. Supernovae typically occur within a few million years of a star's birth, but the Cartwheel starbursts might be synchronized in waves, with whole cohorts of stars reaching their demise simultaneously. If most exploded during an era when Earth-based telescopes weren't looking, we could be living in a temporary lull, like arriving at a party just as the last guest leaves. Alternatively, the galaxy's peculiar magnetic fields might be disrupting the supernova mechanism itself, preventing the shock waves from breaking free of their dying stars. The most haunting possibility, the Cartwheel might be a graveyard with invisible tombstones. If neutron stars or black holes born from supernova are kicked outward by asymmetric explosions, they could now drift unseen in the galaxy's outskirts, their birth events lost to time. Every missing supernova whispers the same unsettling question. Are we misunderstanding how stars die in extreme environments, or is the universe simply better at hiding its endings than we ever imagined? Until we peer deeper through the dust or catch the next cosmic farewell in the act, the Cartwheel's silent stellar disappearances will remain one of its most persistent puzzles. Light from distant galaxies doesn't just pass through the Cartwheel, it bends, stretched by the galaxy's gravity like a funhouse mirror in space. This cosmic lensing effect should, in theory, reveal exactly how much mass the Cartwheel contains. But something's off. The distortion isn't as strong as predicted, as if the galaxy's gravity is playing by different rules. It's not just a measurement error. This anomaly persists across multiple observations, challenging our fundamental understanding of how mass warps spacetime. One explanation digs into the unseen architecture of the galaxy. Most of a galaxy's mass comes from dark matter, which doesn't emit light but bends space with its gravity. If the Cartwheel's dark matter is spread unusually thin, perhaps scattered by the collision, its gravitational grip would weaken, producing subtler lensing. Think of it like pressing a finger into a deflated balloon versus a taut one. The same force creates less distortion. Some models suggest the intruder galaxy's passage could have dragged dark matter outward, leaving the Cartwheel's core oddly light. Yet there's a twist. Alternative theories propose we might not need dark matter to explain this at all. Could gravity itself behave differently in extreme environments like post-collision galaxies? Modified Newtonian dynamics, or MUND, suggests gravity's strength might vary under certain conditions, bending light less than general relativity predicts. While controversial, the Cartwheel's faint lensing adds fuel to this decades-old debate, offering a real-world test case where conventional models fall short. The plot thickens when you examine where the lensing fails. Background galaxies glimpsed through the Cartwheel's outer ring appear slightly more distorted than those behind its core, a mismatch that hints at uneven mass distribution. If the ring's starbursts are anchored by dense gas clouds, their extra mass might amplify lensing locally, while the core's apparent missing gravity could reflect its stripped dark matter halo. Alternatively, turbulence from the collision might have scrambled spacetime's curvature in ways we don't yet have equations to describe. What makes this anomaly so thrilling isn't just the mystery, it's the stakes. If dark matter is truly redistributed here, it could reshape theories about how collisions alter galactic skeletons. If gravity itself is at play, we might need new physics to account for it. Every subtle bend in the light of those background galaxies carries a coded message about the universe's hidden rules, and the Cartwheel, ever the enigma, seems determined to keep us guessing. Beyond the Cartwheel Galaxy's visible chaos, astronomers have stumbled upon something hauntingly beautiful: the faint, rhythmic pulsing of plasma waves rippling through its halo like a cosmic symphony. These aren't literal sounds. Space is a vacuum, after all, but rather oscillations in ionized gas, patterns so regular they've been translated into audible frequencies. revealing a hidden layer of structure in what once appeared to be formless void. The result, a ghostly choir of electromagnetic notes, each one betraying secrets about the galaxy's magnetic fields and the turbulent weather of intergalactic space. These plasma waves aren't random noise. They're organized into distinct bands, each corresponding to different densities and temperatures in the halo's ionized gas. Some pulses mimic the deep, resonant hum of a cello, signaling regions where magnetic fields are strong enough to sculpt the plasma into slow, rolling waves. Others chirp like high-pitched violins, marking areas where charged particles race along field lines at near light speeds, creating rapid flickers in the electromagnetic fog. By decoding these oscillations, scientists have mapped the Cartwheel's halo with unprecedented precision, uncovering magnetic tendrils stretching far beyond the galaxy's visible edges, some so delicate they'd snap if exposed to the slightest interstellar breeze. But the real revelation lies in what these songs imply about the galaxy's surroundings. The waves don't just reflect internal activity, they're shaped by external forces like intergalactic winds buffeting the Cartwheel as it moves through space. Certain frequencies spike in sync with incoming streams of gas from nearby galaxies, while others dim where the halo collides with invisible cosmic currents. It's as if the plasma is whispering real-time updates about the Cartwheel's celestial environment, a live feed of intergalactic weather patterns no telescope could directly observe. The most mesmerizing feature, these oscillations aren't static. Over years of observation, their pitch has subtly shifted, revealing how the collision's aftermath continues to reverberate. Some regions grow louder as magnetic fields tighten, while others fade into silence where the plasma disperses. This dynamism hints at an invisible choreography, a dance between gravity, magnetism, and cosmic radiation playing out on scales so vast they dwarf human comprehension. What makes these plasma waves so extraordinary isn't just their existence, but their persistence. Most galactic halos are too diffuse to sustain such coherent oscillations. The Cartwheel's ability to sing likely stems from its collision, which injected the halo with enough energy to keep the plasma agitated, like a struck bell that refuses to stop ringing. Every note carries a timestamp, a clue about how long it's been since the catastrophic encounter, and how much longer this celestial melody might last. As astronomers refine their instruments, the Cartwheel's symphony grows richer, each newly detected frequency peeling back another layer of mystery. These aren't just random vibrations, they're the galaxy's way of communicating its hidden life, a language of pulses and waves waiting to be fully understood. And with every listen, we're reminded that even in the silence of space, there's music, if only we know how to hear it. The Cartwheel Galaxy doesn't just glow with starlight, it crackles with an invisible storm of cosmic rays, high-energy particles racing through space at nearly the speed of light. But unlike the crisp, structured radiation patterns seen in most galaxies, here these particles create a bizarre, foggy haze that blankets the entire system unevenly, like static distorting a radio signal. This isn't just background noise, it's a frenetic energy field with spikes and voids that defy easy explanation, hinting at forces at work we've yet to fully understand. At the heart of the mystery is the haze's strange distribution. Cosmic rays typically trace the paths of their birth, supernova remnants, pulsar winds, or black hole jets creating concentrated streams or bubbles. Yet in the Cartwheel, they're smeared across vast, diffuse regions, with some areas buzzing with activity while others lie eerily quiet. The outer ring, despite its explosive star formation, contributes less to this haze than expected, as if something's absorbing or scattering the particles before they can spread. Meanwhile, the galaxy's core, seemingly calm, invisible light pumps out a steady undercurrent of high-energy particles, suggesting hidden turbulence beneath its placid facade. One theory points to the collision's lingering chaos. When the smaller galaxy tore through the Cartwheel's center, It didn't just stir up gas and stars, it may have scrambled the galaxy's magnetic field into a labyrinth of twists and turns. Cosmic rays, which are charged particles, don't travel in straight lines. They follow magnetic field lines like trains on rails. In this tangled web, particles could be ricocheting unpredictably, trapped in electromagnetic cul-de-sacs that diffuse their energy into a fog rather than allowing it to funnel into clear channels. Picture a flashlight beam bouncing through a hall of mirrors. The light doesn't travel far before it's scattered in all directions, yet the haze isn't entirely random. Delicate filaments within it hint at unseen structures, perhaps shock waves from ancient supernova or the faint imprint of the intruder galaxy's passage. Some of these filaments align oddly with the spokes of stars stretching from the core, as if the galaxy's visible and invisible skeletons are intertwined. Others spiral loosely around the outer ring, tracing paths that might reveal how energy leaks from starburst regions into the wider galaxy, the most startling possibility. This cosmic ray fog might be fueled by something even more exotic: dark matter annihilation. Though speculative, some models suggest the collision could have concentrated dark matter in certain regions, where collisions between these invisible particles could produce showers of cosmic rays as a byproduct. If true, the haze wouldn't just be a side effect of stellar violence. It'd be a shadowy signature of the universe's most elusive substance, flickering in the darkness. What's clear is that this haze is more than just galactic static. It's a living energy map, charting how violence and magnetism shape a galaxy's hidden energetic landscape. Every distorted filament, every quiet void tells a story, one written not in light, but in the whisper of particles pushed to the brink of physics. And until we decode its full message, the Cartwheel's cosmic ray fog will remain one of its most compelling enigmas, a reminder that even the invisible can shape the fate of the cosmos. Amid the Cartwheel Galaxy's swirling chaos, one anomaly stands out like a sapphire dropped on black velvet, a detached, blisteringly blue region drifting just beyond the galaxy's main ring. This so-called blue blob defies easy categorization, a cosmic puzzle piece that refuses to fit. Its color alone is a dead giveaway. That electric blue hue signals a firestorm of newborn stars, hotter and more massive than our sun, burning fiercely against the void. But how did this stellar nursery end up so isolated, unmoored from the galaxy's other star-forming regions? The answer could rewrite how we understand galactic collisions and their aftermath. One compelling theory casts the blob as a stellar refugee, a massive star cluster violently ejected from the Cartwheel's ring during the collision. Picture two galaxies colliding like wrecking balls, their gravitational forces flinging debris in all directions. If the shockwaves from the impact were uneven, they might have hurled an entire stellar nursery outward, sending it careening into intergalactic space like a spark from a grindstone. Supporting this idea, the blob's motion suggests it's not just drifting passively, it's moving with enough speed to escape the galaxy's grip entirely. Yet it's far larger than typical runaway clusters, raising questions about how such a dense structure could survive the ejection intact. Alternatively, the blob might not be an escapee at all, but an intruder caught mid-merger. Some astronomers argue its chemical fingerprint matches that of dwarf galaxies, suggesting it could be the mangled remains of a tiny neighbor, ensnared by the Cartwheel's gravity during the collision. As the dwarf's gas compressed under tidal forces, it may have ignited a burst of star formation, turning the blob into a temporary beacon. If true, this would make it a rare, smoking gun for hierarchical galaxy assembly, the process where large galaxies grow by cannibalizing smaller ones. The blob's stretched-out shape hints at this violent past, with tendrils of gas streaming behind it like a comet's tail, remnants of the dwarf's unraveled structure. Then there's the wild-card scenario, a rogue gas cloud, adrift for eons, that stumbled into the collision's crossfire. The Cartwheel's shockwaves could have slammed into this primordial cloud like a hammer striking an anvil, triggering rapid collapse into stars. Unlike the other theories, this one posits the blob wasn't born from the galaxy at all. It's an outsider transformed by the chaos. Intriguingly, its metallicity, the abundance of heavy elements, is slightly lower than the Cartwheel's ring, supporting the idea of an independent origin. If confirmed, it would show how galactic collisions can awaken star formation even in the most unexpected places, turning cosmic nomads into temporary lighthouses. What makes the blue blob truly fascinating isn't just its origin, it's its fate. Most ejected structures disperse over time, their stars scattering like dandelion seeds. But the blob's density suggests it might survive as a bound cluster for billions of years, a celestial orphan wandering the cosmos long after the Cartwheel's ring fades. Alternatively, if it's falling back toward the galaxy, its return could fuel future star birth like a boomerang of stellar potential. Every observation peels back another layer, but the blob guards its secrets fiercely. Whether it's a runaway, a merger remnant, or an awakened wanderer, one thing's certain. In a galaxy already brimming with oddities, this sapphire splash might just be the most enigmatic of all. Light from the Cartwheel Galaxy's ring isn't just bright, it's twisted, its waves oscillating in unexpected directions that leave astronomers scratching their heads. When scientists measured the polarization of this light, the preferred direction in which its electromagnetic waves vibrate, they found patterns that defy typical galactic behavior. Instead of aligning neatly with the ring's structure or the galaxy's magnetic field, the light appears scrambled, as if passing through some invisible cosmic filter. This isn't just a quirk of observation, it's a clue pointing to hidden forces warping the very fabric of the galaxy's environment. One compelling explanation lies in the Cartwheel's mangled magnetic fields. Normally, a galaxy's magnetic field lines follow its spiral arms or disk, creating predictable polarization patterns as starlight scatters off dust grains aligned with those fields. But here, the collision's violence likely shredded this order, twisting magnetic fields into chaotic knots. Light traveling through this turbulent electromagnetic landscape would ricochet unpredictably, its polarization scrambled like a message passed through a room of funhouse mirrors. Some regions might even exhibit Faraday rotation, where magnetic fields gradually twist the polarization angle as light journeys through ionized gas, adding another layer of distortion. Yet magnetism isn't the only suspect. The galaxy's infamous dust clouds, thick with debris from the collision, could be playing a trick of their own. When dust grains are asymmetrical, they tend to align with magnetic fields like compass needles, polarizing light in a specific direction as it passes by. But in the Cartwheel, these grains might be stacked in unusual configurations, their orientation scrambled by shock waves or turbulent gas flows. Imagine trying to read a book through a pane of frosted glass that's been cracked and reassembled haphazardly. The text would still be there, but distorted beyond easy recognition. Similarly, the dust's chaotic arrangement could be imprinting bizarre polarization signatures on the escaping light. The plot thickens when you examine where the polarization anomalies are strongest. Curiously, they cluster in regions where the ring's starburst activity is most intense, suggesting a feedback loop between star formation and electromagnetic chaos. Massive stars emit fierce radiation and stellar winds, which can both amplify and disrupt local magnetic fields. In turn, these tangled fields might channel or scatter light in ways that further alter polarization. It's a cosmic game of telephone, where each step from star birth to magnetic turbulence to dust alignment introduces new distortions, leaving the final signal nearly unrecognizable. Perhaps the most tantalizing possibility is that we're seeing multiple effects at once: magnetic twists, dust scattering, and even contributions from hidden cosmic rays or plasma waves. The Cartwheel's polarized light might be a composite portrait of its entire disrupted ecosystem, each layer revealing a different facet of the collision's aftermath. Decoding it fully could unlock secrets about how galaxies redistribute energy and matter after catastrophic encounters, not just here, but across the universe. For now, though, this polarized puzzle remains a shimmering enigma, a reminder that even light, the universe's most reliable messenger, can carry cryptic meanings when the cosmos decides to bend the rules. Globular clusters are supposed to be the universe's ancient relics, tightly packed spheres of stars dating back to the early cosmos, often older than the galaxies they orbit. But in the Cartwheel Galaxy, some of these clusters break the rules, sparkling with a youthful blue glow that suggests they're far younger than the galaxy's catastrophic collision. It's like finding a medieval castle with a neon sign out front. The timeline just doesn't add up. How could clusters brimming with young stars exist in a system where the defining trauma happened hundreds of millions of years ago? The answer might rewrite what we know about how galaxies recycle their stellar legacies. One possibility is that these clusters are true newborns forged in the aftermath of the collision. When the intruder galaxy plowed through the Cartwheel's core, the shockwaves didn't just ignite starbursts, they might have compressed gas into ultra-dense knots, birthing globular clusters in a single, violent surge. Imagine a tornado sweeping through a junkyard and accidentally welding scattered metal into polished spheres. Nature's chaos sometimes creates precision. These second-generation globulars would carry chemical signatures of the collision itself, higher metal content from the enriched gas of the Cartwheel's disrupted disk, a cosmic fingerprint setting them apart from primordial clusters. Yet there's a twist. Some of these youthful-looking clusters might not be young at all. Instead, they could be ancient clusters that underwent a cosmic facelift. During the merger, tidal forces might have ripped apart older globulars, scattering their stars while leaving their cores intact. As these stripped cores plowed through the Cartwheel's gas-rich ring, they could have captured fresh material, igniting new rounds of star formation that mask their true age. Picture a centuries-old tree sprouting vibrant new shoots after a storm. It's still old at heart, but rejuvenated on the surface. Spectroscopic studies could settle the debate, as truly young clusters would lack the telltale alpha elements like magnesium produced by early generations of stars. The most intriguing outliers are clusters caught mid-transformation, their outer layers teeming with young stars while their cores harbor stellar populations far older. These hybrid clusters might be the missing link, showing how mergers can breathe new life into ancient structures. If confirmed, they'd prove that globular clusters aren't static fossils, they're dynamic systems capable of reinvention. That revelation would ripple beyond the Cartwheel, suggesting that what we call globulars might be a diverse family, with some members defying the classic definition entirely. Whether they're cosmic infants or revitalized elders, these clusters hold a mirror to the Cartwheel's turbulent history. Their very existence challenges the tidy labels we assign to stellar populations, reminding us that in a universe ruled by collisions, even the oldest objects can wear a disguise. And as telescopes peer deeper into their starlight, one thing becomes clear. In the Cartwheel Galaxy, time doesn't flow in a straight line. It twists, loops, and occasionally starts over. The Cartwheel Galaxy's core tells a silent story, one written not in what we hear, but in what we don't. While most galaxies with similar histories blast radio waves from their central black holes like cosmic air horns, the Cartwheel's heart whispers. This radio silence is eerie, a stark contrast to the chaotic symphony of its star-forming ring. It's as if the galaxy's supermassive black hole has been muted, leaving astronomers to wonder. Is this a temporary lull or evidence of an entirely different kind of cosmic engine? Dormant black holes aren't unheard of, but the Cartwheel's quietude is puzzling given its violent past. When galaxies collide, the resulting turbulence usually sends gas flooding toward their central black holes, powering frenzied activity. Think of it like shaking a soda can before opening it. The pressure has to go somewhere. Yet here, despite the collision's chaos, the black hole remains oddly subdued. One possibility is that the impact actually starved it. The intruder galaxy's trajectory might have slingshotted gas outward instead of inward, like a celestial thief stealing the black hole's lunch. Without a steady diet of material to heat and accelerate, the black hole's radio emissions would fade to a faint hum. But there's a twist. Some galaxies with quiet cores hide advection-dominated accretion flows, exotic states where gas spirals in so slowly it never gets hot enough to shine brightly in radio waves. Instead of forming a glowing disk, it's like pouring sand through an hourglass, one grain at a time. The Cartwheel's black hole might be operating in this stealth mode, consuming material too efficiently to leave traces of its meal. Supporting this, X-ray observations reveal faint, flickering emissions from the core, suggesting trickles of gas still reach it, just not enough to wake the beast entirely. Then there's the timing dilemma. Black hole activity cycles over millions of years, flaring and fading like a hibernating volcano. The Cartwheel's collision might have triggered a past outburst now fading from view, its radio jets withering as fuel reserves dwindle. If so, we're catching this galaxy in a cosmic intermission, the curtain temporarily drawn between acts. Alternatively, its magnetic field, scrambled by the collision, could be suppressing radio emissions entirely, like a tangled wire disrupting a signal. The silence isn't just absence, it's a clue. By studying what the Cartwheel lacks, we're learning how black holes respond when the universe upends their routines. Whether it's a dormant giant, an efficient feeder, or a delayed reactor, its quiet core speaks volumes, reminding us that sometimes the most revealing secrets aren't in the noise but in the spaces between. Among the Cartwheel Galaxy's swirling disorder, an unexpected pattern emerges, delicate, ribbon-like filaments of dust stretching symmetrically from its core, as if the cosmic collision left behind a set of celestial fingerprints. These so-called mirror filaments defy expectations, their near-perfect symmetry standing in stark contrast to the chaos surrounding them. After a cataclysm violent enough to reshape an entire galaxy, how could anything remain so orderly? The answer might lie in hidden forces weaving structure from the wreckage, proving that even in destruction, the universe has a knack for balance. At first glance, these filaments appear almost artistic, twin tendrils curving outward like the arms of a cosmic ballet dancer frozen mid-pirouette. Their symmetry is so precise it suggests an unseen hand guiding the chaos, a phenomenon rarely observed in post-collision galaxies. Normally, such events leave debris scattered haphazardly like shrapnel from an explosion. Yet here, the dust seems to have arranged itself with intentional elegance. One theory points to the collision's unique geometry. If the intruder galaxy struck at a perfect perpendicular angle, the resulting shockwaves could have propagated symmetrically, compressing gas and dust into these mirrored arcs. Picture dropping a stone into a still pond. The ripples spread uniformly in all directions. In the Cartwheel's case, the stone may have hit with such precision that the galaxy's debris folded into harmonious patterns rather than random clumps. But geometry alone doesn't fully explain the filament's persistence. Enter magnetism, the galaxy's invisible sculptor. The Cartwheel's magnetic fields, though scrambled by the collision, might have retained enough coherence to channel dust into these symmetrical streams. Charged dust particles acting like iron filings near a magnet could have aligned along surviving field lines, creating these eerie mirror images. It's a cosmic version of shaken sand settling into intricate patterns on a vibrating plate where chaos and order collide to produce something unexpectedly beautiful. Then there's turbulence, an unlikely architect of symmetry. Normally, we associate turbulence with disorder, but under rare conditions, it can generate self-repeating structures. The collision may have birthed standing waves in the galaxy's gas, akin to the harmonic vibrations that create symmetrical patterns in a Chladni plate. These waves could have shepherded dust into parallel streams, their rhythmic oscillations imprinting order onto the chaos. Supporting this, some filaments exhibit slight variations, tiny kinks and bends that hint at interference patterns like overlapping ripples in a pond. The most tantalizing possibility, these filaments might be temporary cosmic illusions, their symmetry a fleeting alignment in the eye of the beholder. From our vantage point, dust clouds at different depths could overlap in just the right way to create the illusion of mirrored structures, even if they're not physically connected. It's like two separate rain showers appearing as one continuous storm when viewed from a distance. Future observations with 3D velocity mapping could reveal whether these filaments are truly paired or merely a trick of perspective. Whatever their origin, the mirror filaments challenge our assumptions about galactic collisions. They remind us that destruction doesn't always erase structure. Sometimes it reveals new forms of order hidden in the chaos. And as telescopes continue to dissect their delicate arcs, one thing becomes clear. In the Cartwheel Galaxy, even dust has a story to tell, written in symmetrical whispers across the void. The Cartwheel Galaxy's dazzling chaos won't last forever. Like all things in the cosmos, its mesmerizing rings and turbulent star factories are temporary, fleeting brushstrokes in a much longer celestial story. But what happens next? Will this galactic oddball settle into a familiar spiral, collapse into a smooth elliptical, or forge an entirely new destiny? Simulations and observations of similar galaxies suggest the Cartwheel's fate hinges on a cosmic tug-of-war between gravity, momentum, and the lingering echoes of its violent past. Most ring galaxies, given enough time, eventually relax into spirals. The outer ring's gas, currently ablaze with star formation, will gradually disperse, its stellar nurseries fading as raw material gets exhausted. Meanwhile, gravitational forces will tug the galaxy's lopsided structure back toward equilibrium, smoothing its edges into graceful arms. Imagine a pebble dropped into a pond. The ripples might start jagged, but they eventually soften into gentle circles. Some models predict this transition could take another billion years, with the Cartwheel's spokes dissolving and its core reasserting dominance as a spiral's bright hub. But there's a catch. The Cartwheel's extreme asymmetry and missing dark matter might short-circuit this process. Unlike typical ring galaxies, its core isn't just quiet, it's strangely disconnected from the outer frenzy, as if the collision severed the gravitational conversation between them. Without this link, the galaxy might never fully reorganize. Instead, it could stall in a transitional state, becoming a cosmic zombie, neither spiral nor elliptical, but an enduring oddity trapped between phases. Observations of similar systems, like the less famous but equally peculiar AM06444741, support this idea. These galaxies seem frozen in time, their rings persisting far longer than models predict, as if nature itself can't decide how to classify them. Then there's the wildcard scenario, total dissolution. If the collision stripped enough dark matter, the Cartwheel stars might never fully rebound into a cohesive structure. Instead, the outer ring could fray into a loose swarm while the core shrinks into a compact elliptical, a galactic divorce with no reunion. Recent simulations at the Harvard-Smithsonian Center for Astrophysics show this outcome in about 12% of cases, particularly when the intruder galaxy was small but dense, like a cosmic bullet punching through without leaving enough gravitational glue behind. Yet perhaps the most fascinating possibility is that the Cartwheel is birthing an entirely new galactic species. Its unprecedented mix of features, the ghostly outer halo, the backward spinning gas clouds, the magnetic chaos, might steer its evolution down uncharted paths. Some researchers speculate it could become a polar ring galaxy, where stars and gas orbit perpendicular to the main disk, or even a Hogue-type object, a rare class of galaxy where a ring floats almost independently around a central core. Every telescope observation adds another piece to this puzzle. By studying how similar galaxies age and how the Cartwheel's own structure shifts over decades, we're glimpsing the future of a cosmic icon. One thing's certain, whether it fades into familiarity or defies categorization forever, the Cartwheel's next act will be anything but ordinary. And in its slow transformation, we're reminded that even the universe's most stunning spectacles are just scenes in a much grander story still being written. From its colossal, star-studded ring to its eerily silent core, the Cartwheel Galaxy is a masterpiece of cosmic contradictions. We've journeyed through its 30 strangest phenomena, each one defying expectations and rewriting the rules of galactic evolution. There's the lopsided starburst ring, blazing brighter on one side like a cosmic campfire caught in a windstorm. The ancient metal pore core that stubbornly resets the clock, refusing to catch up with the galaxy's youthful outskirts. The ghostly infrared halo, a whisper of dust stretching far beyond where theory says it should. The rogue gas cloud spinning backward, the gamma-ray hotspots with no visible source, the missing supernova that vanish without a trace. Every layer of this galaxy serves up another puzzle. Then there are the deeper enigmas, the ones that don't just challenge what we know about galaxies, but how we study them. The faint gravitational lensing that hints at missing mass or perhaps flaws in our understanding of gravity itself. The mirrored dust filaments, symmetrical to an almost artistic degree, as if the cosmos paused mid-collision to sketch a fractal. Even the silence speaks volumes, the central black hole's radio quietude, the plasma waves humming in frequencies we're only learning to decode. And let's not forget the phantom companion, the intruder galaxy that seems to have evaporated into the void, leaving behind only gravitational breadcrumbs. What makes the Cartwheel so extraordinary isn't just its individual oddities, but how they interlock. This galaxy isn't a collection of quirks, it's a single, sprawling experiment in extreme astrophysics. Every anomaly connects to another, painting a portrait of cosmic chaos with unexpected order lurking beneath. It's as if the universe took a textbook, ripped out the pages on galactic evolution, and scribbled in the margins. Actually, it's more complicated. And that's the real gift of the Cartwheel. It reminds us that the universe is always more imaginative than we are. Just when we think we've figured out the rules, a galaxy like this one comes along and tosses them out the airlock. So here's my challenge to you. Pick your favorite strangeness from the Cartwheel's menagerie. Was it the runaway blue blob, the dancing dwarf galaxies, the superstar clusters that shouldn't exist? Drop it in the comments, and while you're there, tell us what cosmic mystery you'd unravel next. Because the Cartwheel isn't just a galaxy, it's an invitation. An invitation to stay curious, to question, and to remember that out there in the black, the next great enigma is always spinning into view.